Chapter 2, Exercise 25. Hints. Follow the given hint. First prove that K has an at most countable base. Then, show that every metric space with an at most countable base is separable. We have replaced countable with at most countable in view of comment to example 22. Solution. We first prove that the space K has a countable base. For each positive integer n, consider the covering of K by all neighborhoods n 1 over n of x, where x element of K equaling this. Since K is compact, this covering admits a finite subcover. That is, there exists a point here in K such that K equals this. For every n and n, and I equaling 1, 2, and so on to mn, define V of ni equaling this. We claim that the collection here forms an at most countable base for K. Since this is finite for each n, and we take the countable union over all n element of n, the collection remains at most countable by the corollary to Theorem 212. Now, let G be an open subset of K and let x element of G. There exists delta greater than 0 such that this. By the Archimedean property, we can choose an integer n greater than 2 over delta. Since K equals this, there exists an index I such that this, which implies this. For any this, we obtain the following. Thus, this implying that this. This shows that our collection forms an at most countable base for K. Next, we prove that any space X with an at most countable base set Vn is separable. If one of the sets Vm is empty, we can remove it from the collection while still retaining a base. Thus, without loss of generality, we assume that all sets Vn are non-empty. For each n, choose a point xn element of Vn. Define the set D equaling this. Since D is an at most countable union of singletons, it is at most countable. See also corollary to Theorem 212. To show that D is dense in X, let y element of X and delta greater than 0. The neighborhood n delta of y is open, and hence can be written as a union of some Vn's. In particular, there exists some Vn's, subset of this, and since xn element of Vn, we have xn element of this. Thus, for every delta greater than 0, this, which implies that y element of d bar. Since y was arbitrary, we conclude that d bar equals x, so x is separable. Comments. In solving this exercise, we have established that every compact metric space is totally bounded. See the comment to example 24. The Hausdorff criterion states that any totally bounded and complete metric space is compact. The notion of completeness is discussed in Chapter 3 of the book. The separability of a compact metric space can also be proved differently. By Theorem 237, every infinite subset E of K has a limit point. According to example 24, this implies that K is separable. Thanks for watching.